Swastiastu. Assalamualaikum warahmatullahi wabarakatuh. Salam Namo Buddhaya. In this video, I will explain about chapter 11, Metallurgy for the Non-Metallurgist. But first, I want to introduce myself. My name is Dr. Putra Hutabarat with student ID number 23055310075. I am from mechanical engineering study program from engineering faculty and Udayana University. This main reference, the second edition. Okay, chapter 11, tall steels and high-speed steels. Tall steels belong to a special category of steel alloys that have been developed to manufacture the tools, dies and molds that shape, form, and coat cup other steel alloys. They are also used to process many non-ferrous metals and in some cases non-metals such as machinable ceramics and polymers. Tool steels can be hardened through heat treatment, and their chemical composition have been carefully balanced so that proper heat treating practice impart the combination of properties that enable these grades of steel to function effectively in their intended applications. 11.1 A brief history. The modern story of tool steels began with Benjamin Huntsman, a clockmaker from Sheffield, England, who is credited with developing the crucible melting process in 1742. This process made it possible to produce cast steels with carbon levels that fell between those of cast iron and wrought iron. These cast steels could be hardened through heat treatment, and in the early 1800 they were the best tools available for cutting and machining other metals. The Tailor White steel demonstrates an ability to retain hardness and at the elevated temperatures that are normally encountered during metal cutting operations, which permitted much higher cutting speeds, widths, and depths of cut to be used during machining. This new tungsten carbide alloy was demonstrated at the Paris Exposition of 1900 and was so effective that it virtually made every other tool steel in the world obsolete. The development of this revolutionary alloy opened the door to the metallurgical research that eventually produced many of the advanced grades of steel used in tooling applications throughout the world. Next. 11.2 Modern alloys. Many complex high-alloy alloy tall steels and high-speed steel were developed in the early 20th century following the success of Tailor and White. They still contained, among many other elements, relatively large amounts of tungsten, molybdenum, vanadium, manganese, and chromium. 11.2.1 Tall steel properties. Attainable hardness is the capability to reach a specific level of hardness through heat treatment. Individual tool steels and high-speed steels can be heat treated to achieve a wide range of hardness values that often exceed the hardness capabilities of other types of heatable steels. Red hardness, also referred to as hardness, is the capability to retain hardness and elevate temperatures. The ability of high-speed steels to cut and machine other steels depends critically on their ability to maintain their hardness so that they do not plastically deform under. Toughness is the ability to resist breakage, chipping or cracking under impact loading. Toughness may be viewed as the opposite or brittleness. Tall steels and high-speed steels are designed to achieve sufficient levels of toughness for their intended application. 11.2.2 Grade classification. There are presently more than 40 classifications of high-speed and tall steel alloys according to the American Iron and Steel Institute, or AESE. When these are compounded by the number of domestic manufacturers, the total number of individual steel in these categories exceeds 150. According to the AESE classification system, each group of steel possessing similar chemical compositions and properties is identified by a capital letter. Next. 11.2.3 Effects of alloying elements. The T-series alloys contain 12 to 20% W with chromium, vanadium, and cobalt as the other major alloying elements. The M-series contains approximately 3.5 to 10.5% molybdenum with chromium, vanadium, tungsten, and cobalt as the other main alloying elements. Carbon is by far the most important of the alloying elements and is very tightly controlled. The carbon content of any single high-speed or tall steel is usually fixed within narrow limits, but variations within these limits can cause important change in the resulting mechanical properties and cutting capability. Silicon up to the levels of approximately 1%. The influence of silicon on high-speed and tall steels is relatively minor. Increasing the silicon content from 0.15 to 0.45% provides a slight increase in maximum attainable tempered hardness and has some influence on carbon morphology, although there generally seems to be a concurrent slight decrease in toughness. Cobalt. The main effect of cobalt in high-speed and tall steels is to increase the red hardness feature 11.1 and 11.2, which increases the cutting efficiency when high tooling temperatures are encountered in service. Cobalt generally elevates to solidus temperature and in sufficient concentration may raise the heat treating temperatures that are required as a result. Next. 11.3 Raw tool steels. Raw hot work tool steels, many manufacturing operations involve punching, shearing, and forming of metal at high temperatures. Hot work steel drop age have been developed to withstand the combination of heat, pressure, and abrasion associated with such operation. Raw cooled work tool steels. Cooled work tool steels, because they do not have the alloy content necessary to make them resistant to softening at elevated temperature, are resistant to applications that do not involve prolonged or repeat heating above 205 to 260 degrees Celsius or 400 to 500 degrees Fahrenheit. There are three categories of cooled work steel: air hardening steels, also called Group A, high carbon, high chromium steels, also called Group D, and oil hardening steels, also called Group O. Other non-machining work tool steel grades, in addition to the hot and cooled work steels described: shock resisting steels, low alloy special purpose steels, mold steels, and water hardening steels are also used for non-machining application. Next. 11.4 Effects of alloying and carbides on wear resistance. The wear resistance of high-speed steels and tool steels is strongly dependent of the amount, type, size, shape, and distribution of the alloying carbides that are present in the microstructure. The function that these carbides serve can be understood through the use of an analogy. Consider the appearance and function of a copper stone rod. The alloy carbides that appear in the tool steel microstructure figure 11.3 serve a purpose that is comparable to the function of the wear resistance. A copper stones in the rod, they provide a very hard contact surface area that is extremely resistant to abrasion and wear. Next, the wear resistance of tool steels generally increases with increasing carbide volume percent and carbide hardness. Figure 11.4 is a graphical comparison of the hardness of various alloy carbides relative to the hardness of martensite and cementate, and table 11.5 provides the element distributions in M and associate Rockwell C hardness values for each or of these carbide types. As shown, the precipitate metal carbides such as MC and M2C can attain very high hardness, and they contribute significantly to the wear resistance of tool steels that are alloyed to contain large volume fractions of these particular carbides. Next, 11.5 heat treating high speed and tall steels. High speed and tall steels intended for heat treating are normally prepared in a relatively soft condition with minimum hardness and maximum ductility, known as a periodized annealed condition. The annealing practice used to achieve this condition produces a relatively uniform distribution of the alloying carbides within the microstructure. These carbides may be thought of as repository for alloy content that is available for contributing to the hardening response of the matrix during heat treatment, because as the steel is heated to the austenizing temperature, austenite will form and the carbides present in the steel microstructure will begin to dissolve back into the austenite. Consider figure 11.6, which presents data showing the fraction of several alloying elements that have dissolved from the carbides into the austenite as the austenizing temperature is increased in an M4 high-speed steel. This steel contains three main carbides in the annealed condition: M23C6, M6C, and MC. Next, the secondary hardening response that allow many high-speed steel to possess good red hardness is due to the precipitation of fine alloy carbides or tempering figure 11.7. However, the precipitation process requires that the alloying elements have been dissolved back into the austenite during the austenitization step. It is apparent from figure 11.6 that quite high austenitization temperatures are required to dissolve the MOWV alloy carbides of high-speed steels. The recommended heat treatment practice for tool steels and high-speed steel is much more complicated than that used for the plain carbon and low alloy steels. As evident from the previous examples, careful control of the austenitization temperature, time, and furnace atmosphere are required to achieve a properly heat-treated microstructure. Retained austenite can also be an issue with some of these grades. For example, D2, when properly heat-treated and tempered, normally contain as much as 20% retained austenite in the microstructure. Next, 11.6 powder metallurgy tall steels. As a result of pronounced ingot segregation, conventional tall steels and high-speed steels can contain a somewhat coarse, non-uniform microstructure accompanied by relatively low transverse toughness properties. The carbide segregation observed in the longitudinal section of annealed M2 high-speed steel bars, figure 11.8, illustrates the degree of segregation. Figure 11.8 this illustrates the degree of segregation that is normally present in the dash bars and how it becomes more pronounced as the diameter of the bars increases. Advantage of PM high-speed steels compared to their raw counterparts include better machinability, better grindability, better dimensional control during heat treatment, and superior cutting performance under difficult conditions where high edge toughness is essential. Temper resistance or red hardness is largely determined by the composition and growth of the secondary hardening carbides and is promoted by vanadium, molybdenum, and cobalt. Next, temper resistance or red hardness is largely determined by the composition and growth of the secondary hardness carbides and is promoted by vanadium, molybdenum, and cobalt. These elements can be used in larger amounts in PM high-speed steels than in raw steel without degrading properties. The uniform distribution and small size of these carbides in PM high-speed steels represents an important toughness advantage that is especially important in interrupt cutting where micro-caving of the cutting edge can occur. Next, 11.7 cutting tool coatings in several cutting and machining applications used in industry. It is not uncommon to surface treat high-speed steel and tall steels with specialist coatings to reduce frictional contact, reduce thermal conductivity, and improve wear resistance. These hard wear-resistant surface coatings are often used as a means of improving tool life. There are many surface treatments and treatment processes that are available. For example, it has been estimated that up to 60 to 70% of all carbide tools are now coated. The surface hardness produced by a number of different types of coating is shown in figure 11.10. The material to be machined is an important consideration when selecting a coating. For example, titanium nitride or TNEN coatings work well on various materials but immediately break down when machining titanium. Thin film diamond coatings work well when machining aluminum but are totally ineffective with various alloys. Next, multi-layer coatings have also become commonplace, some of them proprietary to their suppliers. The basic theory underlying the use of multiple coating layers is that each layer has its own function. One layer may have high hardness, another chemical wear resistance, and another oxidation resistance. Material used to make up The various layers of a multi-layer casing depend on the application. Layers may consist of several different materials or may be alternating layers of only a few materials. Such thin layers are considered nanofilms, and thus alternating layers may effectively retard to the growth and propagation of cracks, resulting in increased tool life. Okay. I think that I can explain about chapter 11. If there are error in reading, please forgive me. And thank you for watching my video. And the last, Om Swastiastu, Assalamualaikum warahmatullahi wabarakatuh, Salam Nama Budaya, and thank you.